Welcome to Physics and Happy New Year. Thanks for being here. We are going to start our energy unit. So, here is today with our energy introduction. As you go through, I'm going to provide a little bit of information for you to learn about energy and common forms of energy. So, here, one, I've given you kind of a definition, but it's not a real definition, and then that's going to come down later with the little video. But in brief, energy is due to motion or potential to cause motion. So we talked a lot about motion in quarter one, a little bit of quarter two before moving on to waves, which waves still had motion aspects to it, and now we're focusing on energy as so just keep that in mind. It is related to motion. Uh, Next, with the common forms of energy, I also included kind of what you might call their symbols. So instead of writing out kinetic energy over and over and over, you might refer to it as K. Okay, E thermal. So anytime you see a capital E and then this subscript symbol, that will tell you the type of energy or the form of energy. So kinetic energy, if you've never heard of that, is motion. So anything that is moving has kinetic energy. And so that can include sound vibrations, but just motion in general. Heat, we tend to refer to as thermal. So something can have thermal energy. Well, in fact, all things have thermal energy because if it didn't, then it would be absolute zero. But that's another story. So everything has some form of thermal energy. Gravitation potential, and what that really refers to is, let's say I lift this mouse up in the air. Okay, it now has potential energy from gravity because the moment I release it, we know what's going to happen. It's going to fall. Okay, and so when it's on a table and it's just sitting there, it does not have the potential to fall. It doesn't have gravitation potential energy. But now I've changed its position. I've lifted it up. Now it has potential energy. So same thing, kind of concept goes with elastic potential. You have a rubber band, let's say, just sitting there. Uh, it doesn't have elastic potential stored. You start to stretch it and you develop the tension, right? You increase the tension in the rubber band, and you're going to notice that the elastic potential increases because when you let go, it's going to snap, right? And so you can increase the elastic potential energy when you stretch it. Then there's also a form of chemical potential, and chemical potential energy has to do with chemical reactions, right? And the breaking apart of chemical bonds. So we're going to focus less on that. That will be a huge focus, I believe, in chemistry. Okay, so we're going to focus less on that, but we will really kind of focus on these first four and really gravitational, elastic, and kinetic energy. So then, with that, a little bit of intro, you're going to watch this video. Okay, it's only a couple minutes long, but it'll go in with more details and more examples of energy and the different types of energy. I mean, we talk about energy all the time. You know, our lights require energy, our bodies require energy. You know, so how can energy really relate to all of those things under the same definition? So, you'll find out in the video. And then I want you to put the definition of energy in your own words. Next, I wanted to focus on a very important law of physics, okay? A very important rule. And it's called the law of conservation of energy. And so energy can neither be created nor destroyed. It only can be transferred or transformed. It can change its form. So, for example, you have kinetic energy. I'm moving my hands. And with friction, if you don't know, friction will create thermal energy, heat, right? And so I am transforming energy into heat right now. Next, to do this, I want us to do a little PhET lab. So, okay, so this is Energy Skateboard Lab. You're going to click this link. Okay, open the link and select intro. So just walking you through this real quick. If I open the link, I select intro. Okay, and this is your setup now. Direction number 2, check the boxes: bar graph, grid, and speed. So in the top right corner, we have bar graph, grid, and speed. The grid, you can see, kind of helps you get distances or height, if you will. Your speed, you'll notice, will go up and down. And this is a bar graph here that you'll notice will go up and down. So then follow the directions in each question below. So question number 2 here. Click and drag the skateboard to the top of the ramp. Before pressing play or anything, just look at the bar graph and what do you notice about the energy present when the skateboarder is in this position. So again, I'm going to click and drag and lift the skateboarder to the top of the ramp. Ooh. Let's try that again. There we go. Maybe you might have to push pause. So top of the ramp, notice speed is 0, and we have some information here. Okay, so I just want you to write in your own words, what do you notice? Okay, keep in mind this is potential energy due to gravity. This is kinetic energy, which would be motion. Thermal energy, which be created from the wheels. And honestly, right now we don't need to worry about thermal energy. I'm not going to ask about it. So I think this little trash can, if it is showing up, you can click it and it'll get rid of the thermal energy. But that would be basically the wheels and the ramp are creating thermal energy or transferring thermal energy. I shouldn't say created. It's transferring energy into heat. So again, what do you notice about this? Question 3. Now press the play button. Try to stop the skater when they reach the 3 on the grid. Look at the bar graph. What do you notice about the energy present when the skateboard is in this position? So the 3 on the grid would be about right here or right here. And it'll go back and forth. So honestly, if you miss it, you can do slow motion. Okay, it's about on the 3. It doesn't have to be perfect. And so now what do you notice? Okay. Number 6, now press the play button again and try to stop the skater when they reach the 0 on the grid, the very bottom of the ramp. Oh, look at that. I did pretty good. Okay, what do you notice? Number 5. So now that we've done, we actually don't have to do really much more. What is the relationship between kinetic energy and velocity? So select all that are true. When you look at then the hints that I'll give you is when you look at the kinetic energy and you look at the speed, what do you notice? Okay, and if I take this up here, no kinetic energy, look at the speed. So again, when there was a lot of kinetic energy, oh yeah, that's the thing with this program. If you click and drag and just put this person here, they have no energy. But if you play it, then you'll see the motion. Okay, and again, high kinetic energy and the speed. So you're looking at the relationship there. And you can try, and it's multiple choice. It's actually select all that are true. So there are more than one option that are true. Number 6, what is the relationship between potential energy and height? So, okay, I'm 0 meters off the ground. There's my potential energy. I lift it up here as high as possible, and I have more potential energy. Oh, look at that. I can actually keep going. Okay, so what's the relationship between potential energy and height? Oh, look at that. It falls straight down. I've never tested that. That's funny. Okay, so again, select all that are true. Number 7, now press play and let the skateboarder go back and forth. So really, that is assuming you do a normal routine. Okay, press play, let it go back and forth. Maybe I'll click normal. Okay, what do you notice about the total energy in the system as a skateboarder goes back and forth? So we have kinetic and potential. You can see here going boom, 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 back and forth. What do you notice? And then a couple questions for you, or a new introduction. This was an energy flow diagram, is what we're trying to learn, and we're going to use a scenario of a bungee jumper. So, for an example, okay, this is an energy flow diagram. Okay, that's kind of what we're referring to here. So I'm going to go ahead and close that. Uh, and so then I have some labels, but you're going to be creating those bar graphs on your own. I then have information about energy transfer, and I give you an example with the bungee jump. So, make sure you read those carefully, and it should help you answer the questions below. So, in the following questions, use the bar graph to model the transfer or transformation of energy in the energy flow diagrams. So, here's a little picture. Okay, position 1. This dude is at the top of the jump, and he hasn't jumped yet. So I'm going to ask you to model the potential energy, the kinetic energy, the elastic energy, and then the total energy of the system. And this situation would be the system. So then he jumps off, and you can see he's falling. The bungee cord is not tense yet. Okay, maybe a little bit, but he's falling about a quarter, about 3/4, and then this is the end of the height. It's not the ground, okay, but he comes close to the ground, or the person comes close to the ground. So again, we want to focus on the energy flow. So how that works, if I go into show my work, I have embedded these little models for you. Again, EG is energy due to gravity, and that's really gravitational potential energy and kinetic energy, because this jumper will be moving, and so you'll see that the kinetic energy will need to increase. And then the bungee cord, okay, is going to have elastic energy, and then the total in the system. Okay, and so if I'm here at position 1, this is what you're going to do. So graph the energy flow at the initial. So something to keep in mind, there's different ways you can do it. You can color it in if you want. I might recommend making rectangles and trying to use the colors to model it. But that being said, I think I'm going to use different color. No, I'm going to use this. So I'm going to match my color in the total system with my person for the jumper right now. Okay. Then here's the thing about the total, right? We just watched it. The total energy in the system is not going to change. Okay. And then, oh, I should have done that first. I apologize. Let me try that again. Fill shapes. There we go. Okay. So if you select fill shapes and do a square or rectangle, you can do that really quick. So the entire energy of the system is from the jumper at this point, and it is also entirely potential energy. Okay, so that's the secret. I'm going to force you to think about the other ones, but that's the secret to this first one. It's all potential energy. This person is just standing or sitting here at the top, ready to jump. So there's no kinetic energy, there's no elastic energy, It's all gravitational potential energy. Okay, so then uh, as an example, though, okay, just to show you an example, uh, and maybe I can go back. There we go. Let's just say it looks something like this. And then orange. Okay. Let's say it looks something like this. So this it means that the energy, the potential energy, is lowering and transferring into motion, but it's also transferring into elastic energy. It's transferring into, excuse me, the bungee cord. So if this is the case, I put these dotted lines in to help you, okay, to break it into fourths. So I hope you notice that. So we have a half and a fourth, and then we have a fourth. And so how I want you to represent that on the model would be 3/4, and you can just kind of cover it up. That'd probably be the easiest way. But 3/4 of your total system energy is going to be from the jumper between potential and kinetic. And then 1/4 of your energy in the total, again, the total system is going to be the elastic energy in the bungee cord. Ooh, I said red, green, and blue. I don't know why I said that. Um, you can use the colors like I used, or you can use the colors here. That probably would have been better if I paid attention. That's funny. But anyways, so you'll see that the combination to get to the total system is going to change based on where they are in the scenario, and this will really test if you're understanding how the energy is transferring and making these predictions. Okay, something to keep in mind as well. Uh, this is in 4 different positions. Okay, so position 1, position 2, which is about a quarter. Okay, and that's very on purpose. That's very intentional based on our graphs that are broken into quarters, 3/4, and full. Okay, so I want you to think about that as you're doing this activity. Okay, and then again, so what would the energy diagram, flow diagram look like in position 2, position 3, and then in the final position? Okay, let me know if you have questions, and I hope to see you in class.